Good afternoon. We are the Intersection Simulation Group. I'm Mark.
I'm Alan.
I'm Patrick. So today we're going to discuss what the intersection simulation project is. Our goal for this project was to develop a smart city intersection simulation which mimics the intersections between 120th and Broadway and 120th and Amsterdam. In the orbit room at WinLab, we have a physical scale model, 15:1 scale, of these two intersections, and our virtual simulation is based off of that. Our goal for this simulation is to be a test bed for self-driving research. What this means is we want to have a self-driving car be able to practice in this virtual environment instead of in a physical environment. A couple of reasons for this are, it's less costly, more safe, but also it lets us be a little bit more flexible in what we can do and what options we have for this self-driving research. One of the things that we wanted to accomplish with this is to have a human driving element in this simulation. And the way that we chose to emulate this human driving is via a traffic simulator. The ways that we did that and what technologies we utilized for that will be explained later in the presentation.
So to create a realistic testbed, we utilize three main technologies. First is Sumo, the simulation of urban mobility. Sumo is a traffic simulator. This is what we use to create our traffic models with various routes. The idea was to simulate daily traffic that the two intersections may see in real life. We also use Gazebo, a robotic simulator. We use Gazebo to build our entire world out. So this is where you can visually see the roads, lanes, and cars in 3D. A big part of our project was not only to build a world in Gazebo, but also connect it to Sumo, so we could have the traffic models built in Sumo be seen in our 3D world in Gazebo. To do this, we use ROS, or Robot Operating System, to communicate between Sumo and Gazebo. The specific version of ROS we used was melodic.
So here are images of the physical model intersection at the orbit room in WinLab. These intersections are an accurate model of the intersection in New York, and we based our virtual model on these intersections. On the left, you have an overview of both intersections, and the closer one here is Amsterdam and 120th. The right image gives you a closer look at the intersections of Broadway and 120th. You can see from both images that the roads are not just straight lines, but instead there are other elements such as crosswalks, parking spaces, and traffic lights. Here are the images for our Gazebo model intersection, or the virtual ones that we created. The top left image is a virtual model of the intersection of Broadway and 120th, and the top right image is a virtual model of Amsterdam and 120th. You can see that these are very similar to the physical models in the orbit room. In the overview on the bottom right, you can see that besides these intersections, there are also roads on the outer limits of the model. While these are not actually present in the actual New York intersections, these serve as the path for the model cars in the simulation to exit and re-enter to keep the simulation in constant motion.
This is a video of our Sumo traffic model. Here we can see the traffic lights on both intersections are operational. Notice how the cars attempting a left turn creep up into the intersection, mimicking drivers in real life. You can also see that there's more traffic along the vertical roads. This is because Broadway and Amsterdam are major avenues, while 120th Street is only a minor cross street. Currently we are only using passenger cars, but could explore different models with other vehicles in the future.
Okay, and here we have the video for the results of our hybrid simulation, and we can play the video. So as we see here, we're loading up the hybrid simulation. We have Gazebo load up. As you'll see soon, the world is actually empty right here. I'll explain what's going on there in a minute. We also have the Sumo road network, which will open up in a second. This is what Alan was talking about in the previous slide. We've slowed it down here so that it's not loading too much into the Gazebo at once. As we see here, we have cars running in the Sumo traffic network. And as you see, cars spawn in Gazebo in response to the cars driving in Sumo. So this is the primary goal of our connection, which was to get the Sumo cars on our Gazebo world simulation. Now, as I mentioned earlier, one of the problems we have is the fact that the Gazebo world is empty. What we were working on throughout the last couple of weeks is the implementation of this hybrid simulation based off of a paper someone wrote a couple years back. And one of the problems we ran into is our Gazebo world wasn't compatible with this simulation for one or two reasons, whether it be the models were not quite importing correctly or our world's a little bugged. Regardless, the point of this video is to show that the important part was the connection between the Sumo world and the Gazebo world was established. And one of the things that we'd like to work on as future work ideas is rebuilding the Gazebo world in the template provided by the old paper providers. This would let us have a Gazebo world where the Gazebo world will spawn properly, and you'll still have these Sumo cars being spawned in the Gazebo world.
The end goal of our project was to incorporate the self-driving car group's work with our work. Their self-driving car would then have the opportunity to drive around our simulated environment, and we would be able to see how it handles common traffic rules such as traffic lights, lane mergings, and right-of-way. Another thing we would add in the future is street parking and pedestrians. If you notice in our simulated world, the bottom right picture, there are street parking spots along the 120th Street, as well as crosswalks. To provide a more realistic simulation, we could add these features into our traffic model via Sumo. Lastly, we would sync our Sumo traffic lights with the model in Gazebo using TrackEye, Traffic Control Interface. And we would like to thank Jenny Shang, Ivan Seskar, and Mario Garzon.